in mathematics, Center for Distance Education, Shivaji University, Kolhapur. Today I will discuss the Lagrange's equation of motion for non-holonomic equation, constant from the Lagrangian formulation, post topic of classical mechanics, and which of MSc post and semester post. One more example for non-holonomic constant and find out Lagrangian equation of motion. 2 mass points of mass m1 and m2 are connected by a string passing through a hole in a smooth table so that m1 rests on the table surface and m2 hangs suspended. Assuming m2 moves only in a vertical line, what are the generalized coordinates for the system? Write down the Lagrangian of the system. Reduce the problem to a single second order differential equation and obtain a first integral of the equation. Consider a particle in XYZ system and P of r theta with a point making an angle theta with the x-axis, so that let L be the length of the string and OX be the initial line. Let R theta be the position of the particle of mass m1. Therefore, OM is equal to L minus R. Thus, the system is specified by two generalized force coordinates R and theta. The kinetic energy of the system is the sum of the kinetic energies of the two masses and is given by T is equal to 1 by 2 m1 r dot square plus r square theta dot square plus 1 half m2 r dot square. Potential energy of the mass m1 is 0 and potential energy of the mass m2 is minus m2 gl minus r. Therefore, Lagrangian of the system becomes L is equal to T minus V and 1 by 2 m1 r dot square plus r square theta dot square plus 1 by 2 m2 r dot square plus m2 g l minus r. Lagrangian equations corresponding to the generalized coordinate r and theta respectively reduces to d by dt of da by l by da by r dot plus d by dt da by l by da by r is equal to 0 and d by dt of da by l by da by theta dot minus da by l by da by theta is equal to 0 and so on. m1 plus m2 r double dot minus m1 r theta dot square plus m2 g is equal to 0 and m1 r square theta dot is equal to constant h. These are the required equation of motion, and eliminating theta from this equation, and we get m1 plus m2 r double dot minus h square divided by m1 r cube plus m2g is equal to 0. This is the required single second order differential equation of motion. Now to find the first integral of this, and we multiplying by 2 r dot and integrating with respect to t, and we get m1 plus m2 r dot square plus h square h square divided by m1 r square plus 2m2gr is equal to constant. This is the required first integral of the motion, which represents total energy of the particle. Next, one more example. A body of mass m is thrown up an inclined plane which is moving horizontally with a constant velocity v. Use Lagrangian equations to find out the focus of the position of the body at any time t after the motion set it. Consider a plane inclined moving horizontally and with a constant velocity v. Therefore, the at some instant the distance moved by the plane AB is given by OA is equal to VTV multiplied T. Let at t is equal to 0 the body of mass m be thrown up an inclined plane AB. Let P be the position of the particle at an instant t where AP is equal to R, and if xy are the coordinates of the particle at P, therefore x is equal to A plus AP cos theta, x is equal to Vt plus R cos theta, and y is equal to R sin theta. Not theta is a fixed angle. Therefore, kinetic energy of the particle is given by T is equal to 1 by 2 m x dot square plus y dot square, and potential energy is given by 2r dot v cos theta. Therefore, minus 2r dot v cos theta. Therefore, Lagrangian of the system is given by L is equal to 1 by 2 m v square plus r dot square plus 2r dot v cos theta minus mgr sin theta. R Lagrange's equation of motion is given by d by dt of d by L by d by r dot minus d by L by d by r is equal to 0. Therefore, r double dot is equal to minus g sin theta, and integrating r dot is equal to minus g sin theta multiplied t plus c1. At t is equal to 0, r dot is equal to u, the initial velocity of the particle with which it is projected, and c1 is equal to 0. Therefore, r dot is equal to u minus g sin theta t. Integrating r is equal to ut minus 1 by 2 gt square plus sin theta plus c2. At t is equal to 0, r is equal to 0, c2 is equal to 0. Therefore, r is equal to u2 minus 1 by 2 gt square sin theta. And the locus of the position of the particle is given by r square is equal to ut minus 1 by 2 gt square sin theta bracket square, that is x minus vt square plus y square. This is the our today's task.